Hi, in this lecture, we will be learning about two very important topics. One is data imbalance problem, and then why accuracy is not a good metric. So we'll learn about different other metrics such as precision, recall, F1 score, and at the same time, we'll be also learning how to deal with the data imbalance problem. So the definition of accuracy is number of correct predictions divided by number of correct and incorrect predictions. Okay. So the question is that is accuracy a good metric? It's not always the case. Okay, and we will learn about a specific case, what you call the data imbalance problem. Okay, so in another video, I have explained a particular problem, what you call a credit card fraud detection, and I strongly suggest that you go and check the notebook and the video, because that's where we explain through a practical example. Okay. In that notebook, we explained about our regular modeling setup. It can be a logistic regression model, or it might be a random forest or SVM model. But when we were using classification accuracy as our metric, it turned out to be that the model was doing good for one class, but it was actually not actually doing bad in the other class. Okay. So even the accuracy was 99.89%, but it turned out to be that it was not detecting the actual fraud case more than 2/3 of the cases. So in summary, the model is not working. Okay. So here we have two issues. One is the data imbalance issue and also the metric that we are using. Okay, so that's why we created a common video for these two concepts. Okay. Let's first learn that what are other metrics we can use for these kind of setups. So first, let's clarify some terms, and then we will use those terms to define other metrics. Okay. So here I have defined some terms. True TP is true positive, true negative. So that means that how many cases the model actually was able to detect the level as it was 1 and as it was 0. Okay, so true negative and true positive. It is actually matching with the previous definition. Okay, so number of correct predictions, number of correct and incorrect predictions. Okay. So this plus this sum is our correct predictions, and all the sums are actually the denominator. Okay, so this is the formal matrix definition that we will follow for other definitions. Okay, the level was positive and then model predicted as positive. So this is what we are calling true positive. And then likewise, the level was negative and the model predicted as negative. So this is true negative. Okay, and then the level was positive, but the model predicted as negative, so it's false negative. And then this one is level was negative, but the model predicted as positive, so it's false positive. Okay, so that's how the definition of accuracy is coming: true positive plus true negative, true positive, true negative, and then you sum over all, so that will be the denominator. Okay, so now we'll be learning about precision. So precision is also called positive predictive value, and then recall is sensitivity and F1 score. Okay, so these are alternatives of the accuracy metrics. Okay, so precision is actually the true positive divided by true positive plus false positive. So we are actually estimating that how many of the predicted values are true. Okay, so this is the column sum, that will be the denominator. Okay, so how much of my predictions are right? So that's what is called precision. Okay, and recall is actually this true positive divided by true positive plus false negative. Okay, so the sum of this row. Okay, so in terms of summary, it's telling that how many of the true data points the model was able to identify. Okay, and then F1 score is actually a function of this row and this column. So 2 times precision times recall divided by precision plus recall. So this is the F1 score. Okay, so these are the scores that are more intuitive than accuracy, because here we are actually taking care of both the classes. Okay, so now in the second part we'll be talking about how to deal with the data imbalance problem, and I strongly suggest that you actually go through this notebook. So how to deal with the data imbalance problem. Okay, so one of the ways that you can deal with this is through imposing a sampling bias. Okay, what do I mean by that? So there are two techniques, undersampling and oversampling. Imagine that this is the high majority class, and it was covering almost about 99.99% of the data. So if you sample in a regular way, then you will get 99.99% data coming from this class. Okay, so you have to stop that. Okay, so how do you do that? So you actually impose a sampling procedure that even you are getting more data points from here, you try to just take few. Okay, so this is what you will call undersampling. Okay, and then the opposite is oversampling. Okay, so here you will get 0.01% of the data coming from this class. Okay, so you have to actually increase the frequency. Okay, so how do you do that? Okay, so maybe one way is that you copy the data. Okay, so if you copy the data, then you will have more instances statistically coming from this class. So this is what we are calling oversampling. The other way you can do is you can just redefine your objective function. That means that you are actually changing your model learning, you know. So what do you mean by that? So let's say you are not correctly predicting a zeroth class, and then you are not actually correctly predicting a positive class. You have more weight in terms of loss as associated with one class than the other. Okay, in that way you can actually make sure that your model put more priority on class 1. Okay, we can take this regression example to clarify this. So if you recall, this was our linear regression fit, and we were equally weighting all the blue data points. Okay, this is your objective function and this is your error function, but here you are actually equally weighting every data point. So what we are saying that you can just put more weight on one class than the other, so our model will put more efforts to learn this class. So in summary, we'll have learned about how to deal with the data imbalance problem. So two techniques we have learned. One is that you impose a sampling bias. You either undersample the data from a majority class, or you oversample from the minority class, or you redefine your loss function. These are few techniques that you can apply to your data imbalance scenarios. Okay, let me know if you have any questions. Thank you.